questions that I keep seeing. Can I write on the periodic table and the equation sheet? Yes. So when you get these paper copies, you'll have to put your name on them. Basically, at the end of your test, they will be collected. They'll be put in a box for 30 days before they're shredded. So you can write all over them, which is really useful, I think. Will both of the tests be graded? Will I get to keep the best score? No. So if you opt to take the retake, your initial exam will be canceled. It's not going to be scored at all. Only the retake will be scored. And also know that the readers will all do the May 6th assessment at one point, and then there will be separate readers for the retake exam. The test should be written at the same level. They should cover the same concepts, right? You can look at College Board's website, see the breakdown of all the topics that we should see, but they're going to be completely different exams. Can you bring your calculator? Yeah, you can still bring your calculator. Yes, Desmos is built in, but if you prefer to have your calculator in front of you, the one that you've been using all year, bring it. You don't even have to clear the memory of your calculator. Will I get to retake the same FRQs? No. How would that be fair? The FRQs have already been released. So this will be an entirely new exam. So it's written by the same people who wrote the May 6th exam, but it is going to be a completely new exam. Is this going to impact the curve? I think I get this question every couple minutes. No, remember, AP exams are not curved. They are graded based on a comparison of your understanding of the material to the understanding of someone in a college course. So if you understand, let's say 78 of the percent of the material, that's equivalent to a score of a 5. All right, so that's kind of how it goes. AP exams are not curved. So you could do really poorly on purpose and it's not going to impact the score breakdown. We'll just have more ones than we normally do, unfortunately. All right, so keep sending those questions. If you have questions that I did not answer, please put them in the chat and I will be jumping in and responding to these as we prepare for that retake in a week. All right, here's the important part of this conversation. Should you retake it? So I'm telling most students no. And this is why. You put so much time and effort into the May 6th exam. You spend weeks prepping for that. It's a lot of stress involved with that large exam. It's a whole huge chunk of a day. You're ready to move forward. And most students, if you were a 3 student before, you're still going to be a 3 student. It's just not worth it. It's move on, right? You have so much else going on. This is the most hectic time of year, and I hate that this is being offered as something to add to your already overfilled plate. But there are some other perspectives. Let's say you're in a situation where your class didn't quite get through the content in time. You just finished electrochem and you didn't even know what electrochem was before May 6th. Then maybe you'd want to consider retaking the exam because you're more prepared. Maybe the May 6th exam was your first time actually taking a full-length exam and you feel more prepared because you know what to expect. Those would be reasons to retake it. The best reason to actually retake it, right, is if you really were inhibited by the lack of a paper formula sheet. You either couldn't access it, you couldn't find it, you were having issues with it glitching, and you couldn't answer FRQs because of it, then by all means, retake it. Or if you are really, really aiming for that 5 and you feel like after seeing the 2025 exam, you have a better idea of what to expect on the hybrid exam, you feel more prepared, you've continued practicing for other retakes in your class and you're still learning the content at that level, then by all means retake it. So now the question is, how do you sign up? You're going to contact your AP's coordinator at your school to sign up. I'd have a conversation with your AP teacher, make sure that their feelings align with yours before signing up for this so that you are a team with this. Also recognize not all schools are going to have late exam or makeup exams. Your only option is to retake it at the school where you took the initial exam. So it might not be an option to retake it. So just know that that is also a possibility. But if you want to sign up, step 1 is to contact that AP coordinator. All right, and if you choose to retake the exam, the best way to review, right, is to keep diving into all those FRQs. So I'm going to go through this year's released FRQs. I'll spend some time on each portion so you can kind of learn some strategies, and we can talk about some of the trends that I saw on this first hybrid exam that we have seen. All right, let's start with FRQ 1. So this was a mass spec problem, and right away, I will admit, when I jumped down and I sat down and I wanted to jump in and do just average atomic mass calculations. And that's not what this question is asking. So don't be like me. Don't get excited about seeing the mass spectrum and the numbers. drop down to exactly what the question is asking first before you look at the diagrams even. So right away, looking at I, we want to complete the mass spectrum, drawing in thick lines to show the percent abundances of magnesium 25 and 26. So now I'm going to back up. I'm going to say, okay, my goal is to figure out the percentage of each of these. I'm not looking for the average atomic mass. I'm not identifying this. We already know it's a magnesium. I know that magnesium 24 is 79% abundant. I'm going to take 100, that remaining 21% is going to go to those other two isotopes, which are approximately equal. So I'm going to make sure my bars are equal and at about 10.5%. So that's how I'd walk through that. So again, when you see these questions, don't get overwhelmed by the diagram. Don't get distracted. Don't just jump in until you know exactly what the question's asking. You will have up to 5 sheets of scratch paper. Write down notes. Use the tools in Blue Book to flag and highlight, do things like that. Even though it's a hybrid exam, you can still annotate the screen in certain ways. All right, moving on to the next part. This is one of those examples of why knowing the basics is enough to get a 3 on the AP Chemistry exam. You want to describe the difference in atomic structure that accounts for the difference in mass between magnesium 25 and 26. We are just looking at isotopes here, right? What's the difference in an isotope? You probably learned this in Unit 1 in Chemistry 1. It's the difference in the number of neutrons. So both magnesium 25 and 26 will have the same number of protons because they are both magnesium. The difference is going to be 1 additional neutron in magnesium 26. So knowing that we saw mass spec on this exam, I wouldn't be surprised if we saw photoelectron spectroscopy on the retake. You'll have to let me know once you can talk about it, whether or not I am correct with that. All right, so it really is that simple. This is an easy point. Just understanding atomic structure. We're talking about the protons, neutrons, and electrons. So being really specific with your explanation and your justification, including the numbers in there as well. All right, next part, we are already looking at a particle diagram. This one looked a little bit different just because we have the highlighted text here. And also, you could look at this and say, oh, wait, why do we have these 2 beakers? Oh, no, what are we about to do? We're going to combine them. Yeah, eventually we will. But the next 2 questions are just looking at each of the individual solutions. So this first part is Coulomb's law, which I warned you're going to see a lot. And I really like how this question is broken down. You're asked to describe why Na+1 has a weaker attraction to water compared to the magnesium cation. And then you're going to explain that in relation to the relative charge and the relative size of those ions. So you're going to be using Coulomb's law. You can find that on your equation sheets. And it's, again, just force is proportional to the magnitude of charge and inversely related to the distance between the charges. So even if you couldn't remember that relationship, you could find it on your formula sheet and then relate that back. So this is how I would describe it, why this is happening, right? Sodium has a smaller magnitude of charge, +1, versus magnesium's +2. Also, it has a larger radius, and that's why we have the weaker electrostatic forces. Larger radius means it is further away, therefore less of an attractive force. All right, moving on to part C. You're asked to find the pH of the solution in beaker 2. Not the pH of the mixture of the 2 solutions, just beaker 2, which is sodium hydroxide. So what you need to remember is sodium hydroxide, a group 1 hydroxide, this is going to be a strong base. That means it fully separates in solution. It fully ionizes, which means the concentration of sodium hydroxide is going to be equal to the concentration of just hydroxide, the OH minus. So use that to find the pOH. From there, you can then subtract from 14 to find your pH. Then when it comes to sig figs, I tell all my students just stick with 3 sig figs throughout the exam. It's a safe bet. Why do I have 5 here? Well, because with pH, remember, the initial number to the left of the decimal is just the magnitude. You only count sig figs to the right. That's just because pH is a logarithmic scale. All right, moving on to part D. We actually are going to mix these 2 solutions. Hopefully you had this image printed out in your FRQ booklet so you could then use that beaker to write. You didn't have to draw a particle diagram or anything with this. We are just going to find the concentration of Mg2+. So looking at that, if we think about adding Mg2+ plus NaOH, this question says before the reaction takes place. So really what we're going to do is find the moles of magnesium and then divide that by the total volume of the new solution to find our concentration. So just using molarity times volume gives us the moles. We can find the moles of Mg2+. From there, we then divide by the total volume of solution, again, in liters. Remember, you always want to do this in liters. You'll get an outrageously high number of moles if you do not, but that will give you your concentration of I can't see it. I forgot. All right, in part E, we do see KSP, but thankfully you don't have to do an ice table with this. We're not calculating molar solubility or anything like that. We're just writing the expression. So we want to write the expression for KSP. So KSP is going to be the concentration of products over reactants raised to the power of the coefficients. However, with these solubility product expressions, right, your initial reactant is a solid. It's a solid precipitate. Doesn't impact equilibrium. So really KSP is just going to be the concentration of the products raised to the power of coefficients. So remembering to include the charges in there and then the exponents as well. And we use square brackets to indicate the concentration in terms of molarity. So making sure it matches that. All right, in part 2I, we are combining those two and we want to calculate Q. So for this, you have to remember Q is calculated in the same way as K. The difference is Q, the reaction quotient, describes any point other than equilibrium. So we're still going to calculate it in the same way. We have our concentration of Mg2+ from part D. We're going to use that. We're going to use a hydroxide concentration. We're going to square that, and we'll have our answer of 2.07 times 10 to the negative 11. And that's all you need for that point in part 2I. Moving on to part 3I, this is where we want to predict whether or not the precipitate is going to form. If you are looking for that type of prediction, you're going to need to compare Q versus K. So in this case, Q is going to be much greater than K. So because Q is large, not that much, but Q is bigger than K. So because Q is bigger than K, the reverse reaction is favored. So normally when you think about that, you're like, oh, so we're forming more of our reactants? Yes, we are. And guess what? Our solid precipitate is our reactant in this case. So when Q is greater than K, the solid precipitate will form. All right, last part of the first long FRQ. In a separate experiment, the student adds HNO3, which is one of the 7 strong acids that you should know. So what happens when that is added to solution, right? It's a strong acid, so it's going to fully ionize. H plus is going to react with the hydroxide in solution, forming water. What happens to equilibrium when that happens, right? So as that H plus is combining with hydroxide, we're going to form water, and that means that our concentration of hydroxide decreases. So therefore, the reaction is going to favor the production of more of that. And what does that mean? That means more of our magnesium hydroxide is going to dissolve. So as this happens, equilibrium is going to shift for more products, and the amount of undissolved magnesium hydroxide is going to decrease. I would say this is one of the more tricky points on this assessment, but let me know what you're thinking. I want to know what you think was the hardest FRQ in this year's exam. So put that in the comment. I'd love to see what you all think. All right, so some takeaways from FRQ number 1. Read what the problem is asking for first before starting to do any calculations. I made that mistake. I don't want you to lose time making mistakes like that. Also, in relation to that, don't be overwhelmed by the images and diagrams and things like that. Jump right down to what the question's asking, then go back, see what you need from that diagram. All right, moving on to FRQ number 2. This was one that a lot of teachers were talking about because it's been a while since we've seen a combustion analysis problem. You review empirical molecular formulas early in the year, and then you kind of forget about them, right? But knowing the basics again will get you points. So if you look at AI, calculate the number of moles of H2O produced. We're given a mass of water and we just have to convert that into moles. That seems too easy, but that's all you need to do. So we have 2.883 grams of water. We know the molar mass of water. We divide by that, we get 0.1600 moles of water. Maybe this is the hidden sig fig question, which case you want to make sure you have 4 sig figs to match the initial values. So 0.2400, those 2 zeros after are significant. So we want to make sure that our answer has 4 sig figs with this. All right, next part. So for part 2I, we want to find the empirical formula. So to do that, we're going to need moles of carbon, oxygen, and hydrogen. We're told that the moles of carbon and oxygen are the same. So find the moles of carbon first. So we have 0.2400 moles of CO2. If I look at a molecule of CO2, for every 1 molecule, I have 1 atom or 1 mole of carbon. So it's a 1-to-1 ratio. So that means if I have 0.2400 moles of CO2, guess what? I also have 0.2400 moles of carbon. All right, so knowing that I have 0.2400 moles of carbon, I'm also going to have the same number of moles of oxygen. So those are equal. Now I need to find my moles of hydrogen. So I have 0.1600 moles of water. For every 1 mole of water, I have 2 moles of hydrogen, so just double that. So now I have my moles of each of the components of that empirical formula. I need to figure out the whole number ratio. So to do that, you're going to divide all quantities by the smallest value to try to hopefully get to a whole number. We can't have 1.3 atoms of hydrogen in this, so we're going to have to then multiply everything into all our whole numbers. So multiply everything by the same number. If we multiply it by 3, we end up with our empirical formula. So it should be C3H4O3 is the simplest formula. The process for finding an empirical formula, the easiest thing to do is remember this: percent to mass, mass to mole, divide by small, multiply till whole. That is always the process. If you have to take this one step further and find the molecular formula instead, you're going to find the molar mass of this empirical formula first, and then compare that to the molar mass. If you divide the two, you'll figure out how many times you need to multiply the empirical formula to get to the molecular formula. All right, and again, this is just known as a combustion analysis problem. It is just a simple find the empirical formula problem, but because we're starting with the combustion products, you have to take it just one step further to find the moles of each of those elements. And this is what makes the long FRQs so tricky. We just did a combustion analysis problem, and now we're going to do a titration. So first thing I would do with this is quickly identify, am I working with a weak acid, a strong acid, a weak base, strong base? And looking at this, it's given in the question stem. This is a weak acid, and we're titrating that with sodium hydroxide. You'll actually see sodium hydroxide in multiple questions on this assessment. Know that sodium hydroxide is a strong base. You can also look at the titration curve. You'll be able to see that buffer region, and you know you're working with weak plus something strong. So identify that first. Then I would go ahead and mark in the equivalence point versus the half equivalence point. So equivalence point is going to be where the moles of acid and base are equal. It is the vertical slope. So dropping that down, we'll have a volume of 16 milliliters. The half equivalence point is half of that, right? So that will occur at 8 milliliters. And that's important because that's where the pH is equal to the pKa. All right, before I get ahead of myself, I want to go ahead and jump and see what is the question asking. So in part I, we're asked to find the molar concentration of our acid. So with this, we have to recognize we have a 1-to-1 ratio of our weak acid to our strong base. So you could technically use the dilution equation. It's a safer bet just to calculate the moles of base first. Then if we needed to use that molar ratio, we could then easily convert. But with this, we're going to find our concentration of the base times the volume at the equivalence point in liters. That will give us our moles of base. Then to find our concentration of the weak acid, we take the moles divided by the volume, which was, 10 mils, again in liters, and that will give us our concentration. Part 2I. This is the point, this is the one you want to see on this exam, right? So we wanted to determine the approximate pKa. You have to remember at the half equivalence point, that is the magical point where pH is equal to the pKa. Why is that? Because at that point, half of the weak acid has been neutralized by the base. So that means that half of the weak acid is conjugate base. So when we think about the Henderson-Hasselbalch equation, right, that log portion just cancels out, leaving us with just pH equals pKa. So I saw this as a pH of about 4.1. So therefore I wrote my pKa as 4.1. And yes, a range of answers are going to be accepted for this, and that would carry on to the next point as well. All right, so now we get into Henderson-Hasselbalch equation. So you have to remember pH is equal to the pKa plus the log of the conjugate base divided by the weak acid. And if you look in 3I, that's what we're looking for, right? ASC minus, that is the conjugate base divided by that initial concentration of our weak acid. And I said you have to remember this. You don't. It's on your formula sheet. Find it on the formula sheet and write it down. So now what we need to do, normally we'd be asked to solve for the pH, but this one's a little bit different, right? You're asked to solve for that ratio of conjugate base to weak acid, but you can do that, right? So let's plug in what we know. We know our pH is 4.7. We know our pKa is 4.1. And then let's let our concentration of conjugate base over weak acid be equal to X. you're just going to solve for x. So I'm sorry, I just lost my exponents apparently. So that should say x is going to be equal to 10 raised to the power of 0.6, which would give us a final value of 3.98. And again, if you chose that the pH was 4.2, your answer is going to be slightly different to this, but the readers are going to accept a range of values based on that. And error always carries forward. Let's say you said our pKa was, I don't know, 8, right? And then you use that, but you did this calculation correctly. You'll get full credit for that. All right, moving on to C. So this is another situation where I don't want you to get intimidated by vocab that you've never seen. Dehydroascorbic acid. What is that? Guess what? You don't need to know. Drop down to I. The rate law for this reaction is given. Explain how the data supports the conclusion that the reaction is first order with respect to the concentration of that weak acid. So what you're going to do is you're going to go to the trials. You're going to see an instance where the concentration of our weak acid has changed, but the concentration of the other reactant is held constant. So the best situation is going to be looking at trials 1 versus 3. And I see here that I have doubled the concentration in those 2 trials. Now I'm going to look at the rate and see how the rate is impacted by the change in concentration. And thankfully, when this is doubled, guess what? The rate also doubles. Let's say instead the rate quadrupled. That would indicate a second order reaction. So when we're looking at the order of the reaction, it's going to be raised to that power. If the reaction, let's say the reaction doubled, let's say the reaction didn't change, blah, 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 take that part out, right? So now you just need to justify that by saying, okay, when the concentration of our weak acid doubles, the reaction rate also doubles, indicating a first order reaction. In the next part, you're just asked to calculate K. So normally with a capital K, when we're thinking about equilibrium constants, you don't need units. But with rates, the units are really important and can be kind of tricky to figure out. So with this, we're given the rate law expression, so we already know that it's going to be first order with respect to each reactant. So overall, our order is going to be an overall rate of 2 if you added those exponents. So if you have all of those rate constants and units memorized, you could do that. Or just plug in the numbers from this table, right, to then figure out what those units are going to be. So I'm just plugging in my rate is equal to K times the concentration of each reactant, solving for K, finding out that my final units will be inverse molar and inverse seconds. Let's say instead you had inverse, instead of molar, you looked at moles per liter. If you still use that, you'll still get credit for that, right? Those are equivalent units. Both should be correct. All right, part D. This one was another one that I think people are up in arms about because how often do you think about ion-dipole interactions? I feel like most students will define this once and then we don't see it again. But if you think about the initial question, right, the magnesium and water, sodium and water, that was also an ion-dipole interaction. So basically, you just need to recognize the I3 minus has that charge, which means that you're going to have ion-dipole interactions between that charge and so that charged particle and the oppositely charged portion of water molecules. So that's going to interact with the positively charged hydrogen ions. I shouldn't say positive, the partial positive charge on hydrogen ions. So that's what this is. This is not asking you to justify what's going on. It literally says identify. So my guess is that if you just wrote ion dipole, that should be enough to get the point. All right. Takeaways after this second FRQ. Again, don't get overwhelmed by the complicated images and diagrams. Focus on what the question's asking. Start there, then go back up to the diagram if you need to. And that's a preview for what's about to come. So FRQ 3, this was the most widely discussed FRQ, just because no one had seen a diagram like this. But that's the whole goal of these exams, right? College Board wants to push you and see how you respond to material you haven't seen before. So in this, you're just asked to complete this Lewis diagram. So back up to what you know. We have P4. We're going to calculate the total number of valence electrons in this molecule. We're going to count up all of our bonds. We have 6 bonds. We're going to subtract that from the total to figure out how many electrons we need to place. We have 8 electrons remaining. Guess what? Each phosphorus atom is going to get a lone pair. So everything just obeys the octet. We don't have an expanded octet or anything like that. This actually is a really easy point if you didn't get stopped by that diagram. All right, moving on to part B. The reaction of white phosphorus with oxygen is TDF, thermodynamically favorable. So we know overall our delta G is negative, but in part I, we're told delta S is negative, which is the opposite of what we'd expect for a thermodynamically favored process. So thinking about this, we want to explain why the entropy decreases as a reaction occurs. So looking at this right away, I look at the fact that we have a gaseous reactant and a solid product. Also, if you look at the number of molecules, we have 6 on this side, 5 gaseous molecules, and we don't have any on the right side. That's what we're looking for. That would indicate the decrease in entropy or the spread of matter. So this is the official way that I would describe it. Mention those microstates, definitely a buzzword in there. But this is how you would describe that. Then moving on to part 2I, the enthalpy change of the reaction is also negative. So a student claims, and guess what? All 3 students are correct on this exam. A student claims that the reaction is going to be driven by enthalpy. And right away, I want to agree with that because I know the overall reaction is favored, right? So overall, I have a negative delta G. I'm going to think about that relationship, delta G equals delta H minus T delta S. So if delta S is negative, I'm definitely going to need a negative delta H to ensure that delta G is still negative. All right, so this student is correct in their logic. If we had a different situation, let's say we had one where we're asked to figure out which would be, how could we make this a favorable reaction in terms of the temperature? Again, go back to this equation, focus on what you need to ensure that delta G is negative. All right, moving on to the next part. This one, I guess I lost my animations here, but this is another example where you're given a whole lot of information. Really, you just need to focus on what the question's asking. So don't worry about the diagram, just start here. So we want to calculate the amount of heat released during the experiment. So you're going to recall Q equals MC delta T. We're also asked to figure that out in kilojoules. If you look, our specific heat value is given in joules, so we'll have to do a quick conversion before writing that final answer. But it's just a matter of plugging and chugging, right? So our mass is 100 grams. Specific heat, we're told it's the same as that of water. And then our change in temperature is always your final minus your initial. So that gives us a total amount of heat of 158.84 joules. Again, got to change that to kilojoules. So you just divide that by 1,000. I used 3 sig figs with this to match the initial mass because this one only had 3 sig figs. All right, so next up, we want to calculate the delta H of the reaction. And I would say a lot of students get tripped up by this because this isn't something you do too often. And if you're in a situation where you don't know how to calculate something, but you're given the units associated with it, work backwards, right? So I know my answer has to be in kilojoules per mole. I just calculated the kilojoules. Can I change my mass into moles? Yeah, we can do that, right? So change your mass of P4O10 into moles. Then take your kilojoules and divide by the moles to get your answer for that enthalpy of the reaction. But then let's back up. It also asks us to include the sign in your answer. How do we do that, right? This is where we actually care about the rest of that image. So P4O10 reacts exothermically. So that means heat is released. We have a negative delta H, right? So when we think about the sign of heat, it's not that we have negative heat. It's whether heat is lost or gained. If it is lost, we need a negative with it. If it is gained, it will be positive. So therefore, this would be negative 451 kilojoules per mole. All right. Some of the solid P4O10 stuck to the weigh paper and was not transferred to your calorimeter. Given that this is the limiting reactant, how will this impact the change in temperature? I'd argue that of the experimental style questions, this is one of the easier ones actually. So if you think about Q equals MC delta T, if we have measured out a mass, a specific mass, but that's not what we actually added to the calorimeter, and we're asked to calculate Q, we could do that. But this is just asking how this is going to impact the change in temperature. If I'm not adding as much solid, the temperature is not going to change as much. So delta T is just going to decrease. And you just need to be able to justify that. So we don't know how much mass is lost, but less of our limiting reactant in the calorimeter means that the final temperature is not going to change as much as initially. So therefore delta T would decrease. And then next up, we have a delta H of formation question. This is like Hess's law, right? So we're going to add up the pieces of the puzzle to get to that final equation 5. And looking at this right away, I focus on P4. I have 1/4 of that. Looking at this, I know I'm probably going to multiply this by 1/4, and then the PCl3 cancels out, so I'm not going to change this one at all, and then I'm just going to add those two. So whatever you do to the reaction, you're going to do that same thing to your delta H value, and then it's just a matter of adding those two together. So pretty straightforward question. It should be an easy point, honestly. And then we move to a particle diagram. These are tricky, but what I always recommend is just start by counting and labeling the particles that you have. So right away, I have 6 particles of chlorine, 2 particles of PCl3, 4 of PCl5. I know that each particle represents 1 atmosphere of pressure, so let's go ahead and multiply that. And then I'm trying to solve for Kp. So I know that Kp is going to be the pressure of my products divided by the pressure of my reactants. This is just a 1-to-1, so that makes it really easy. You're just going to plug all of that in, and you'll find out that Kp is just going to be 0.333 atmospheres. Technically, I should just have 2 sig figs based on this enthalpy value, but this is why 3 sig figs is always a safe bet. All right, moving on to part 2i. Does the value of Kp increase, decrease, or stay the same when the temperature is increased? Justify your answer based on delta H. So looking at our delta H value, right, it's a negative value. This indicates an exothermic process. When we think about an exothermic reaction, that means that heat is released to the surroundings. It's released as a product. If I increase the temperature, right, I'm then going to favor the reverse reaction. So I'm going to form more of my reactants. So that means the pressure of my reactants is going to increase. And when I think about my Kp expression, right, it's products over reactants. If my denominator increases, my Kp is going to decrease overall. So this is how I would justify that. So this is an exothermic reaction. That reaction is going to favor the reactants when the temperature increases, and therefore Kp will decrease. All right, so we made it through all 3 long FRQs. This is my takeaway for this, right? We've seen a lot of crazy diagrams. I've talked about that after every FRQ. However, what I want you to keep in mind too is you don't have to complete the test in this order. You are free to skip around. Start with the questions you feel most confident with. If you immediately got overwhelmed by the figure you saw on question 2, save it for last. If you know it's going to distract you, don't start there. Start with where you feel most comfortable. There is no right or wrong way to do this. It is okay to answer all the questions that you know how to answer first. All right, let's move on to the short FRQs. So FRQ 4, with this, we're trying to identify the hybridization of the valence orbitals of the carbon atom in the H2CO molecule. So pick one of those, look at it, count the bonds on that specified atom only. So looking at this, we have 1, 2, 3. The double or triple bond will only count as 1 when it comes to hybridization. So then we want to indicate that is sp2 hybridized. So we add up everything to show the 3, right? The 1 is not shown, just like with everything in chemistry. We just ignore 1s, but this would show the 3 bonds to that. All right, in part B, in the diagram provide a single dashed line. Don't be that guy who draws 15 lines. Well, you can't draw 15 lines here, but just focus on the instructions. You just want to show 1 line between the strong hydrogen bonding attraction. Be careful. That's not going to occur between any of the hydrogens bonded to carbon because this is a nonpolar bond. The hydrogen is not going to have a partial positive charge here. You have to look at the one off of oxygen. So this would be an example of the interaction. This is going to be the easiest one to draw, easiest one to connect. Not so easy to connect here to here or here to there, or technically here to here, right? So this is the best option. Just draw 1 single line so that you don't lose points for being obnoxious. All right, moving on. 4C. This one, you're given a lot of data here. Let's focus on what the question is asking. So in part I, we want to propose a temperature to which the mixture should be cooled such that the methanol and H2CO will both be liquids. Just look for a range, right? So right away, melting point, 176 for one, 181 for the other. So it's got to be above that. And then our boiling point occurs at 254. So it's got to be somewhere between 181 and 254. So make sure you're using the temperature in Kelvin, but you just have to give a number there. Not a difficult point, thankfully. All right, in part 2I, the scientist analyzes the mixture after it's cooled and determined that 8.59 grams of methanol is present. Calculate the amount of thermal energy in kilojoules that was removed to condense the 8.59 grams at its boiling point. Oh, look, you're given a molar mass, start there. So immediately convert that mass into moles. Then from there, we are given our value, right, of the enthalpy of vaporization is here, 37.6 kilojoules per mole. We're just doing some quick conversions to get that final answer. Again, making sure that your final answer is in kilojoules. Thankfully, the delta H VAP was given in kilojoules, so that makes this one really easy. So not too bad for that first short answer FRQ. Let's look at the next one. So the next one, we have some obnoxious Lewis structures. But what we're doing in part A is we want to predict the geometry around the atom of silicon. So looking at this, you again are just focusing on the number of bonds and lone pairs off of that atom. So this has 4 bonds, 4 indicates tetrahedral geometry. Pretty straightforward, not even looking at the expanded octet. So now in part B, the student claims that compound Y has a higher boiling point because it has stronger London dispersion forces. Do you agree or disagree? Well, I already told you we're agreeing with the student every single time. So both are going to have dipole-dipole interactions. Both are going to have hydrogen bonding, right, at this oxygen atom here. So they're going to experience hydrogen bonding here. Both cases. The only difference is that central atom, silicon versus carbon. And this is where the polarizability of the electron cloud comes into play, right? So silicon is, if you look at the molar mass too, right, it has a much larger molar mass. This means it's going to have a more polarizable electron cloud, and therefore it's going to have stronger London dispersion forces. That is the difference. In part C, an equal molar mixture of the 2 compounds is heated. When the mixture reaches 82 degrees Celsius, which compound will have the higher vapor pressure? Of course, we're going to see vapor pressure. When it comes to IMF, the stronger the IMF, the higher the melting point, the higher the boiling point, the higher the everything, except vapor pressure. Vapor pressure is the opposite. When the strength of IMF increase, vapor pressure decreases, right? So when we're thinking about vapor pressure, that's the pressure above a liquid as it's about to boil. So when the vapor pressure is equal to atmospheric pressure, the substance boils. So at 82 degrees Celsius, right, compound X is boiling. So that's going to have the higher vapor pressure. So because it has weaker intermolecular forces, it has a lower boiling point, but that's why the vapor pressure is going to be higher at this point. And then the last portion of this FRQ, because, 22% of the exam has to come from Unit 3, is just an ideal gas calculation. So you're asked to find the moles of gas in the container. You're given the pressure, the volume, the temperature, and the ideal gas constant just based on your formula sheet. So it's just a matter of plugging everything in. The only thing you have to convert is the temperature. So you add 273 to that, you end up getting 0.74 moles. If you're stuck on units, always use your gas constant. So the ideal gas constant is going to have liters, atmospheres, moles, Kelvin. Make sure everything else matches that to make sure you're getting the right answer. And we've made it to the dreaded FRQ number 6. This first portion, not too hard. It was parts C and D that had everyone talking, including all of your teachers. So looking at this, we are just asked to write the half reaction for oxidation that occurs at the anode. So let's back it up. Let's read the description here. As the cell operates, the zinc electrode increases in mass and the aluminum electrode decreases in mass. So you're going to remember the cat gets fat. So as the cell operates, right, the cathode is going to accumulate mass. Therefore, the zinc is the cathode. Red cat means reduction happens at the cathode. And oxidation is going to happen at the anode, which is going to be aluminum. So looking at this, this is your reduction half reaction. We're going to flip this to give our half reaction, and that's all you have to do. So you had to pick which one was the anode, and then you had to know that oxidation happens at the anode, and therefore we have to flip this reaction around. Next up, we want to write the balanced net ionic equation for the overall reaction. So we're going to keep that oxidation reaction flipped, and then we're going to add that to our reduction. When we are balancing these redox reactions, you just got to make sure the electrons balance out. Maybe you've practiced balancing an acidic and basic solution in class. Thankfully, that's not covered on the exam, so you'll only just have to balance out those electrons. So we're then going to multiply each by the correct number to try to get 6 electrons. We add those two together, and we have our final redox reaction. And dun dun dun, here's the one that had everyone's head spinning. So initially, each electrode has a mass of 50 grams. We are told the zinc accumulates mass, the aluminum loses mass, but that was really to tell you where the anode versus the cathode was. Which electrode's mass changed the most? So we don't need Faraday's law for this. We're not going to actually calculate the mass accumulating at either electrode. We just want to describe which one changes the most. And that's why this question is so creative, because this is not like anything anyone has seen on previous FRQs. So looking at this, we want to compare aluminum to zinc. And yes, we're gonna compare this in terms of mole ratios. And for every 2 moles of aluminum, I will have 3 moles of zinc. That's all you need to do for this. I know. You don't want to hear that. You want it to be more complicated than that, but this is really all you need to do. So 2 moles of aluminum is going to have a mass of about 52 grams. 3 moles of zinc will have a mass of 196. So as we have lost 52 grams of aluminum, we have gained 196 grams of zinc. Therefore, the zinc electrode's mass is going to change the most. And that's it. That's it. So with this test, you have to recognize that questions are going to be asked in ways that you're not going to expect. And you got to step back, think about what you know, and find ways to relate back to the basics. All right, let's move on to that last part of FRQ 6. So with this, we have a standard cell potential of 0.90 volts. We want to make sure that we are producing a higher voltage. So we have access to all of these half reactions. We have to use the zinc half cell. How can we make the most positive or most thermodynamically favored process? So with this, I'm going to go to the highest cell potential, which is the gold reaction. And then I'm going to say, yeah, I'm not using zinc as my oxidation anymore. I'm going to flip that. That's going to be my reduction. Sorry, I'm not going to use zinc as my reduction anymore. That's going to be my oxidation. So when I do that, I add those two together, I'll get a voltage of 2.26 volts. There is some interpretation for this question though, and we won't really know how it's scored until September. Let's say we had to keep zinc as the cathode. The best way to make this more positive, right, is to combine it with the most negative reduction potential there, because when we flip that as the oxidation, it's going to be more positive. So if that is the case, then we'd want to combine it with the beryllium half reaction to get a voltage of 1.09. My guess is that we can change zinc to the anode. But again, I like to show both just in case. Again, we don't have the official scoring guides and we won't see those until September. All right, we've made it to the final question. With this one, you had to circle the atom that accepts the proton. So looking at this, it's a matter of what we call steric hindrance. Seeing how this oxygen is kind of hanging out by itself, that's the one that's going to carry the negative charge. That's the one that's going to accept the proton. Versus this one here, this one is in the middle of that compound, this one too. Those are all satisfied. It's not normal, right, for oxygen to have 3 lone pairs on it. It normally has 2 bonds. That's why this is our choice. All right, and then the final question. So when this ion reacts with water, it forms an acid according to the following expressions. We have our Kb expression that is given, and we want to calculate Kb for that ion. We're going to use our hydroxide concentration, knowing that the concentration of hydroxide is going to be equal to the concentration of the weak acid at this point. So therefore we can set this up as x squared over that initial concentration of that conjugate base. So knowing that, we just plug everything in, we get our answer for Kb. The next portion asks us then to find Ka. Ka, you got to remember Kw is equal to Ka times Kb. It's just a matter of dividing Kw, that constant, by Kb. We can use the constant because we're at 25 degrees Celsius. And if you don't have it memorized, it is on your formula sheet. So you're just setting that up, remembering to put parentheses around your Kb value so you're not making a silly mistake in your calculator. It's the little things that make a big difference for this to find that Ka answer. Again, this is an equilibrium expression, so you are not going to have units with those answers. This is the one time on the test that I don't want to see units. All right, and the very last portion is that in part C, we have another student response. So we have H3O+. We're trying to decide whether or not this is a catalyst. So looking at this, I would try to find H3O+. You notice it's not in the overall reaction as either a reactant or a product. Looks like it is used in the first step and then released in the second step. So yes, I would agree that this could be a catalyst. All right, so that was all of the FRQs. Then you get to this part where it says stop, end of the exam. And I want you to take a moment just to listen to this. Stop obsessing over your test and your score. You have worked so hard this year. You have learned so much chemistry. And whether you demonstrated that on this exam or not, it doesn't matter. I am proud of you. I'm proud of you for enduring the struggle that is AP Chemistry. And I guarantee you are going to go on. And because of this struggle, all of your other classes in the future are going to seem easier. And that is a wonderful thing. Whether you decide to continue on in science or STEM or medicine or not, like this has been a valuable experience. And I'm proud of you. I'm proud of you, and you should be proud too. And your score will come out in July, and it will be what it will be, and it's okay. This is such a small blip in the scheme of things. So these are some of the trends that I noticed on this year's exam. Of course, this was our first time seeing a hybrid exam, and I will say it seems like the questions were designed in a slightly different way. So really creative thinking in terms of what we were asked to solve for, how we were asked to solve for it. Of course, we saw some unique diagrams. Honestly, we see those every year, though. You have to learn to expect the unexpected, and you can't let it bother you. So thinking outside the box a little bit, but really relying on the basics of chemistry. Again, another situation where 3 sig figs worked throughout the entire exam. Stick with that. And then be really careful with units. On this exam, we saw a lot of questions where you were given constants that had certain units, but then your final answer had a slightly different unit. So just be careful to double check your work to make sure you're remembering to, divide or multiply by 1,000, depending on how you're converting that unit. If you're looking for more help, let's say you've decided to take the retake and you just want some more review, I have a full review from my last chance review that I gave before the initial exam that is linked here. I also have just a final unit, complete unit review along with problem sets and keys, and I'm here to help. Please let me know if you have any questions. Keep putting them in the comments. If you decide to take the exam next Wednesday, I want to hear from you. I want to hear how you're feeling, your concerns, your thoughts, and how you feel about being done with AP Chemistry. I thought we were going to be done by now, but we're so close, so hang in there. And please help me out and keep passing my accounts along. I am just a chemistry teacher who wants to help as many students as possible. I do this for fun. I don't get paid for any of this. I'm in my basement now. What time is it? It's probably like 11. Yeah, it's 11:30 at night. And this is what I do for fun. So help me help more students. Thanks for watching.